Welcome to this video that shows how you can combine POS and CHAMP 3D Integra tools to design a direct radiating array consisting of 10 by 10 conical horns. The array is intended to provide maximum gain over a circular area of 1.5 degrees that'll eventually scan the Earth, which, when seen from geostationary orbit, corresponds to plus minus 8.7 degrees. The frequency band of interest is 12.75 to 14.5 GHz. We'll consider three cases. First, the horns are modeled using the simple Gaussian beam model available in POS. After an analysis with uniform excitations, these are optimized using the optimization tab in POS. Then the horn model is replaced by a more realistic smooth-walled horn designed by CHAMP 3D to have the same taper as the initial Gaussian beam, and the excitations are re-optimized. Finally, the horn profile is expanded in cubic splines, and the geometry is optimized simultaneously with the excitation coefficients. We start with the Gaussian feed model. This is a mathematical expression that mimics the shape of a conical horn fairly well. In the Optimization tab, I've specified the goal of the array optimization to be 37 dBi over an angular region of 1.5 degrees in diameter. The analytical feed model selected in POS is a Gaussian beam with a taper of 3 dB at 9 degrees to ensure a good performance over the Earth. With a simple uniform excitation of the array elements, the minimum edge of coverage over a circle of 1.5 degrees and over the entire frequency band is 35.2 dBi, the red curve. Optimizing the coefficients will distribute the power better and raise the edge of coverage gain by 1 dB to 36.2 dBi, the green curve. So, in summary, the simple mathematical model, which is independent of frequency, gives us 36.2 dBi over the entire frequency band. We'll now start the second case, where we replace the Gaussian feed model by a more realistic CHAMP 3D model for a smooth conical horn with approximately the same taper as the Gaussian model at the lowest frequency in the band. The geometry is generated by the built-in CHAMP 3D wizard. The new horn gives slightly different and actually slightly improved performance over the Gaussian feed. And after a re-optimization of the coefficients, we end with a performance increase from 36.2 to 36.8 dBi. This concludes the second case, and we'll now really be challenging the optimization by moving to the final step, which is to make a more advanced feed design by including the shape of the horn in addition to the excitation coefficients. The smooth horn profile can be described by means of splines, and we can express the spline knot distance from the horn axis in terms of real variables. In that way, we obtain further optimization parameters in addition to the excitation coefficients. Both sets of parameters are now included in the optimization, which of course takes substantially longer since the horn performance needs to be evaluated at each iteration. Still, in less than 1.5 minutes, we obtain a new array pattern with a minimum edge of coverage of 37.6 dBi, that is, an improvement of 0.8 dB over the non-profiled feed horn design. The shaping has an obvious effect on the horn, as can easily be seen in the Feeds and Waveguide tabs when the optimized values for the spline knots are loaded. It would not have been obvious how to specify the horn performance to optimize it independently from the array excitations, which is why the improvements of almost 1 dB is only achieved due to the combination of CHAMP 3D with POS Integra tools. If you're interested in learning more about how to combine POS and CHAMP 3D, feel free to contact us at info@tigra.com. Thank you for watching. I hope you enjoyed it.